about J-cell and differentiation theory. So in particular, I'd like to explain so I recently studied what called the Coulomb branches of the field theory, and today I'd like to explain how I try to explain the definition, our mathematical definition of Coulomb branches. And today I'd like to explain how I arrived at this definition. So this is motivated by topological quantum field theory. I'd like to explain this motivation. Another motivation is the monopole formula, which Amihai explained us, and that is very important, but today I will not mention it. So monopole formula is in somehow in behind. Okay, I first recall the notion of topological quantum field theory. So introduced by Attila Seong. So they somehow axiomatized the quantum field theory. So they understand quantum field theory, which and topological means that the quantum field theory, which depends only on the smooth structure, that is depending on the metric. So they understand, they formulate topological quantum field theory as a functor. So this is a functor from the category of Boltzmann to vector space. And what is a category of Boltzmann? So this is a category. So you have objects and homomorphisms. So objects are d-1 dimension. These are fixed integers. So now soon I will specialize in the case when d equals 3, but so far this is general. So object is one-dimensional smaller manifold and without boundary, and I assume that manifold has orientation. And the homomorphism is a Boltzmann between two d-1 dimensional manifold, so which is just d-dimensional manifold with boundaries, and you have two boundaries, sigma 1 and sigma 2. You also allow the sigma to be empty. Empty set could be also regarded as d-1 dimensional manifold. So if you have closed D manifold, closed D-dimensional manifold, then it is a Boltzmann between empty sets. And this is the category, so you need to consider the composition of the homomorphism. And composition is just given by gluing of this D-dimensional manifold along with the common boundary. You have say similar picture of sigma 2 and sigma 3, and then you connect along sigma 2 to get Boltzmann between sigma and sigma 3. And it has also tensor structure. So if you consider two d-1 dimensional manifold, sigma 1 and sigma 2, then you can consider the disjoint. So if you consider, you regard this as an analog of the tensor product of sigma. And as I said, the empty set is allowed. And if you consider the union of the d-1 manifold together with empty set, then it doesn't change. And it corresponds to the unit object in the tensor product, which is just underlying base field. But here I consider complex vector space. Base field is always complex numbers. So the category, target category is the algebraic category. So you consider category of C vector spaces, and objects are vector spaces, and the homomorphism is linear maps. And the composition of homomorphism is just usual composition. And the tensor product is tensor product of vector spaces and unit objects, as I said, base field, which is number. So TKFT is a functor. So you have Z, so which assigns object to object homomorphisms, and the composition corresponds to composition, and tensor product is respected. So it means that you have D of C, so this is the vector space assigned for the closed manifold sigma. And if you have a Bourdism between sigma and sigma 2, then you have a linear map D of X from D of sigma to D of sigma. And the composition of the Bourdism corresponds to composition of linear maps. And if you have disjoint union sigma 1, union sigma 2, then the corresponding vector space should be tensorful. And for unit object, the corresponding vector space should be base. Any question? Yeah. So the boundary could be disjoint. So you can consider sigma. Then this is and this is empty. So you can consider this as a pairing. And of course, this as I said, so in the integral quantum field theory, it depends on the shape of X for the Riemannian metric on X, and d of X depends on the Riemannian metric. But I assume this to be topological quantum field theory, meaning that it depends only on the structure. So this is a kind of toy model for the quantum fields. And why it is toy model? So I try to explain the motivation. So what is a quantum field theory? So if you have so X is first you consider X the case when X is a closed D-dimensional manifold. So this X is closed to D, no boundary. So you consider the space f of X. This is the space of all fields phi on X. So fields, depending on your choice of quantum field theory, you can consider various fields. For example, space of maps, you fix a target to space T, and then you consider the space of all maps. Or so the simplest case is just to take T to be the real numbers, and it means that you consider the space of all functions. And if you have, for the gauge theory, you choose a compact Lie group G, and you consider the space of all connections. So you consider some very huge. So if X is a usual smooth manifold, but f of X is the space of functions or something similar objects, space of similar objects. So this f of X is very huge space. This is the infinite dimensional space. So you consider f of X as some kind of infinite dimensional manifold. Then this D of X, so this assignment, so for closed D manifold, you should have the homomorphism from the complex number to complex numbers, which is nothing but a complex number. So maybe I should also for closed to closed to manifold. So this is C. So I identify D of X as complex number. In this case. So it means that just multiplication by complex number as a homomorphism. So we should assign, for closed D manifold, we should assign complex number. And this is given by as usual, done in quantum field theory. You consider the Lagrangian, you have a, depending on the quantum field theory, you have the Lagrangian, and you integrate exponential of I times Lagrangian over this space of all the fields. So this gives some complex number, but usually in the quantum field theory, which physicists considers, so this integral is ill-defined. So this is infinite dimensional space, and this d phi is some measure, and it is usually not. You can show that this kind of integral, this measure with appropriate probability doesn't exist on this space. So this is just a heuristic expression, you should regard it. But if you accept this should be some integral over some space, then this should give a complex number. So this is a heuristic definition of the g of x as a complex. And you continue this consideration. So if you have a boundary, if x, d manifold x has a boundary, then in order to do this integration, so you first need to fix a boundary value of phi. Boundary value of the field of phi. So I fix boundary. So phi is a space of map. So if phi is a space of map, phi is a map from x to target space, and if x has a boundary, then you first fix boundary value of phi. Then once you fix phi, small phi, this is boundary condition, then you consider this integral. So this integral is complex number, but the phi could be arbitrary. So it is a function in phi, and phi is a field on sigma. So sigma is a boundary. So if you fix phi, then you get a complex number. So in this way, you get a function on the space of fields on sigma, right? So then g of sigma. So for d minus 1 manifold, we should assign a vector space, and this vector space is defined as a vector space of function arising in this way. So this is how physicists understand. You use quantum field theory to construct the vector space and also find vector in this vector space and also complex numbers for closed field. Any questions? Okay. So as I said, but this integral is infinite dimensional, is an integral over infinite dimensional manifold, and in general you don't have this measure. So this is ill-defined, but it gives some motivation. But in quantum field theory, Atiyah and Seagal originally introduced this concept of quantum field theory because they have some concrete examples of topological quantum field theory, which was at least partially mathematically rigorously defined. Partially means that you usually need to drop some assumptions. So this is a delicate matter which I will not explain. But anyway, so there are examples of topological quantum field theory constructed earlier by Thomas and Flare and Witte and others. So that those works motivate Atiyah and Seagal to introduce this concept of topological quantum field theory. So somehow it means that there's mathematical examples which justify this heuristic quantum field theory definition of g of x and g of sigma. So how it goes? So in the case of Witten's Chern-Simons, which I think that just introduced just before the Atiyah and Seagal introduced this topological quantum field theory. So this case is different, has different flavor. So I will not explain that. this case. But the case of Donaldson flare theory, so this case, they construct basically partial four-dimensional topological quantum field theory. So in this case, because so they consider in physical language, they consider the supersymmetric topological quantum fields. So this makes a difference. So because of supersymmetry, so but this path integral, which is an integral over the infinite dimensional space, is localized to integrals over the minimum of L. So L is a Lagrangian, and the minimum of L. So in the usual quantum field theory, so for example, if you take consider the space of path connecting two points, then the minimum is unique, so you consider line. So in the typical model, minimum is a single point, but for the supersymmetric quantum field theory, you typically has the non-unique minimum of the Lagrangian for some space. So, but not the arbitrary space. Instead of all the space f of x of all fields, you get the finite dimensional space, which is usually called modular space. It is because usually the minimum of L satisfies some partial differential equation. And the space of solutions of partial differential equation is usually finite. So anyway, so by some miracle of the supersymmetry, you get integral over finite dimensional space instead of infinite dimensional. So maybe you can imagine the following scenario. So you know you learn the Stokes theorem for the integration of the differential form of matter. And so here, instead of the integral of functions over with respect to some measure, so you replace, because of supersymmetry, you replace by integration of differential. And this differential form is closed differential. For the closed differential form, the integral is replaced by integral over the boundaries. So this kind of mechanism appears in this supersymmetric path integral. So because in this case, more drastically, instead of the boundary, the integral over the boundary, so the integral is reduced to the integral over the finite dimension. Or maybe so if you learn the Cauchy integral, then you instead of counter integral, so you just compute the residue. So which is a value at the singular point, residue at the singular point. So you have a similar mechanism. So this integral has some special property that instead of integration over infinite dimensional space, you replace it by the finite dimensional. So then g of x. So this invariant is for closed manifold is defined as integral of differential form over modular space, which is finite. Then this is because this is a differential form and this is closed. So this can be understood as a topological pairing between the homology group of the modular fundamental group of the modular space and the cohomology. So you can compute this integral in a topological approach. And the Donaldson invariants of four manifold are defined basically in this way. So there's a technical caveat because the modular space is usually has singularities, so you must somehow justify the definition, even though that this is a finite dimensional space. You need to argue that the singularity doesn't contribute to the integral. But anyway, so this is a technical issue. This is a very rough idea why this topological quantum field theory, which was originally motivated from the quantum field theory, gives a mathematically well-defined invariance as integration of the modular space. And also in this case, Z of sigma. So this vector space is very roughly homology or cohomology group of the moduli square of sigma. And in fact, the flare homology, which gives a Z of sigma in the Donaldson theory, the definition is much more involved than this. So this is just approximation, but I think this is a good intuition. So and also in this, I consider the one-dimensional lower case, and in this case, this is more or less correct. So, and this reason, I hope this, as I said, this is the integration of the closed differential form over finite dimensional manifold. So I think the it is natural to guess that the corresponding vector space should be the space of cohomology group. Okay, any question? Okay, let me continue. So we consider three-dimensional reduction of Donaldson axle, and so Donaldson and Freire consider the space they take SU2 as a gauge group, and they consider the gauge theory, four-dimensional gauge theory. But here we consider the three-dimensional reduction, which is formally you can consider that as a four manifold, we just take three manifold times this one. So this is what I mean by three-dimensional reduction. But I also add some other object, which is photonic representation. In the physics language, this is called hypermultiplet. And this is called the three-dimensional N equal 4 gauge theory, supersymmetric gauge theory. So for the original Donaldson and Freire theory, GC is SU2 and M is equal to 0. So for this choice, you get what Donaldson Freire theory, but we consider the one-dimensional smaller case. So this is a three-dimensional. And then we expect that we can construct the topological quantum field theory from this case. So it means that we should get Z of X complex number for closed three manifold, and Z of sigma vector space for closed two manifold. So this sigma, and if sigma appears as a boundary of three manifold, then Z of X should be a vector. So we expect for given G compact Lie group and the photonic representation, we should get those data satisfying those actions of topological. But as I said, even for Donaldson and Freire theory, some of actions, for example, maybe I will go through. So some of action must be dropped. Otherwise, we don't have. You don't have full topological quantum field. So that is somehow related to the singularity of modular space, which I omitted. So as I said, the modular space is a finite dimensional multiple, but I also mentioned that this modular space usually has singularities. You must be careful to check that this integral is well defined. And this is, in fact, you need some assumption on four manifold. And because of this, you don't get the full topological quantum field. So you need to drop some condition. So this is somehow, there's no general recipe for that. And somehow, although I define the topological quantum field as a functor, but this is not achieved in general. So you must drop some condition. This is delicate part. And so in practice, so for given, if you try to construct topological quantum field theory, you really need to carefully study what the properties of modular spaces and what kind of property you can still have and what property you lose. So you must carefully check them depending on case by case. So for this choice of three-dimensional angle, so you can consider this my recent work on Coulomb branch as an attempt to construct the topological quantum field theory, but still I don't get the full topological quantum field theory, and which axiom I can still have that I cannot arrive at the final goal, but I still have some partial construction. So this is a Coulomb branch, which I have been working on. So this is the current status. So compared to the arbitrary topological quantum field, in fact, we don't get much. So unfortunately, so we so far have a good understanding of the Z of S. This is a vector space associated. Well, you can S2, but S2 is in fact very important. So if you consider three manifold, so this is a three-dimensional vector. If you consider the three manifold, that's the simplest way to construct the three manifold with boundary is remove a point or neighborhood of the point. Then you get S2 as a boundary. This is the very simplest way to construct three manifold with boundary. And so far we understand what is this vector space and what kind of structure we have. And as I will show, this D of S2 has commutative ring structure. So D of S2 is a vector space, but it also equips with commutative multiplication. So G is 3D dimensional topological quantum. So conjecture. So then for sigma is x2, G of sigma is a vector space. But as I illustrated in this in the next picture, so it is equipped with commutative multiplication. So for this construction, you consider this picture. So take sigma, and we take the simplest, very simple three manifold. So I take sigma cross interval, and then as I said, as I did in here, so I take remove a point. So this is a picture. So sigma cross interval, and I remove a point. And as I said, I also maybe I put a small ball around this point, and then the boundary. So here you have three boundaries. Sigma cross velocity is the bottom, sigma cross 1 is the top, and also S2 in the middle. Then by the rule of topological quantum field theory, so you should have a map from 0 to sigma, tensor field. Right? So it should, so I consider D of S, the element of D of S, as an operator of D of sigma. So in the physics literature, so element of D of S2 is called monopole. So D of S2 is represented by some gauge with possible singularity. That configuration is monopole. That connection is called monopole. So anyway, from this picture, G of S2 should have a structure of commutative value. So if you have two singularities like this, then you put sigma in the middle. Then the lower point is the operator. Here the middle, and upper operator gives operator middle to top. So in composition, this if you have two points, then you have an operator from bottom to top as a composition. So from this picture, G of S2 should have multiplication. And here,
what about this?
So this is the picture. So this picture explains the multiplication. So you have this. You put the boundary in the middle. You put the sigma times half at the middle. Then lower bowl. And if you have an element in T of S here, then you have operator from the middle. If you have another operator element in T of S here, then you have an operator. The composite. Yeah. And at least heuristic. And then moreover, this is commutative because so we compose from bottom to up, but so you can so this is the three-dimensional move force freely in the horizontal. So you can switch the force the topological in a smooth path. So it means that this multiplication should be commutative. And moreover, so it said that so far we cannot mathematically rigorously define G of sigma for general sigma, but once it is not from the topological quantum field theory perspective, it is natural to expect that G of sigma should be representation of this commutative. So, as I said, sigma is difficult, but from this, we get G of S2 plus commutative multiplication. So you get some commutative ring. Then you can consider its spectrum in the sense of algebraic geometry. So in algebraic geometry, instead of varieties, people consider space of functions for the affine algebraic variety. So instead of affine variety, people consider the space of functions, this variety, and you can recover the original variety as a space of maximal ideals, commutative ring. So this is a spectrum construction. So you can define some space from as a spectrum of this commutative ring. So in the physical language, G of S2 element of G of S2 is a monopole operator, as I mentioned, and G of S2, a monopole operator can be composite, and G of S2 is a ring of monopole operator, and then consider its spectrum. And this is what physicists call Coulomb branch. And the physicists didn't have this definition, but they say that how to say the Coulomb branch is a spectrum. Well, I mean, I think they basically say the Coulomb branch is the spectrum of the ring of monopole operators. Kind of. This is all the question.
This theory has an activity.
But this is, I was a topological twist. I committed. But in fact, already in here, I mean, I didn't explain properly, but So from one of the from the axiom of political quantum theory, you get basically the figure which I draw here. So you consider the cylinder and the bent into the two boundary, the polarities between the two boundaries of the empty set. So this shows from this topological invariance shows that V of sigma must be finite. So it means that one of the axiom of the topological quantum theory is violated because this is the affine variety. Coulomb branch pieces have been studied in many examples. They are always affine variety, non-trivial affine variety. The space of function is always infinite. So it means that one of the actions must be violated. But in some sense, this is the actually interesting point. Otherwise, we don't get the interesting variety. And this is somehow, how to say, compensate each other. So it's, we get the interesting object Coulomb branch because we drop one of the actions. Okay, by using this intuition, so I, together with Breverman, think about define Coulomb branch as a spectrum of G of S3. And recall that I mentioned that here, G of S2 should be modular space on sigma, or homology of modular space in sigma. And this is how we arrive, we get the commutatively. So in fact, by some technical reason, we cannot directly work on the two manifolds S2. But yes, we consider stress. Okay, let me continue. So I'd like to define G of S2 as a commutative ring, and then once I succeeded to define commutative ring, then I take the spectrum. This is our definition of the Coulomb branch. And as I said, G of S2 should be the cohomology or homology of the modular space on S2. But as I said, by technical reason, I somehow need to replace S2 by its variant. In fact, this is more closer to the original intuition, original physical definition as a modular space, as a ring of monopole operators. As I said, the monopole operator corresponds to singularity at the three manifold. So I consider this model, this space. So I choose a very small disk times small interval, and then I remove the point. So the essential point is the singularity at the point. So I get this very small level. Then I use algebra geometric model for this three manifold. Algebra geometry, complex algebra geometry. So I somehow need to replace three manifold by caricature of the algebra manifold. So I first replace this small disk by four manifolds. So this is okay. This is a disk of radius 0. And I take the interval to very, very small. So then you somehow it becomes this picture. Maybe I can draw here. So this is a formal disk, and I choose very small epsilon. And I choose, so there's some singularity in the middle, and I make epsilon smaller and smaller, and consider the limit. Then I have D, and I have a smaller d, smaller part. So this is the limit of D times epsilon, and this is D times minus epsilon. But somehow you need to remember there is a singularity. So there is singularity here. So this is a picture. It means I take D, so I drop this epsilon. So union of D and D. So here it means I glue two disks along here, but I need to remember the disk so I can glue over the puncture. So this is my caricature for this picture, 3 manifold in algebra. And in fact, the modular space of holomorphic bundles on this space has been studied in the context of geometric representation theory. So this is called affine Grassmannian. So over any disk, small disk, any holomorphic bundle is trivial. So it can be trivialized. This is well known. So you have the trivial bundle, and also you have the trivial bundle in downstairs, and those two bundles are glued along the puncture. So this is a picture. And from this consideration, if you forget the part, this part coming from the section, so the modular space has this description. So in the middle is a space of map from this puncture disk to G. So this is the gluing data of the upper disk and lower disk. So because I removed I glued along the puncture disk, this is a space map from this side. And then I can allow the gauge, I can consider everything up to gauge transform, which means I take quotient out by the space of map from this. So this is the space of gauge. And I have upper disk and lower disk, so I should divide by large. So this is a space, modular space, and this space is called affine Grassmannian. If I remove this second left quotient. So anyway, this affine Grassmannian is an infinite-dimensional analog of the partial fragmentarity and has been used in the geometric representation theory for many years. So in particular, you can people study the homology group of this space, and in fact, so this multiplication is given by the so-called convolution product of this affine Grassmannian, and this has been studied in the context of representation theory. So in particular, the special case when M is equal to 0, so M means M is a section. We consider not only the connection, but we also consider some sections of associated bundle for the case theory, and this M corresponds to this part. And if we don't consider this additional section, then we just get the affine Grassmannian, and its homology group is in fact already studied earlier by Bezrukavnikov, Finkel, and Markovitz. And they studied its commutative ring, and they computed its spectrum. So they get some space called the universal centralizer by this construction. And then this space is very important in geometry. So we just extend the result to general M, but by some technical reason, I need to assume this M is a symplectic representation of G, and M, I assume M is direct sum of N plus N star. But anyway, so this is some technical assumption, and we just slightly replace affine Grassmannian by adding sections of the associated bundle, and we can consider the modular space, and we can compute the homology groups, and can define the convolution product, and in this way we define the field function. And one of the important check of this correctness of this definition is the monopole formula. So this was the one of the motivation for this construction, and in particular, so you can check that this our definition recovers the monopole formula. So this is one of the consistency check of our definition, and so anyway, so our definition is mathematically well defined, and it seems it recovers what physicists have considered for many years. So anyway, this is a construction, but I think this construction is also interesting in mathematical perspective. So for example, we can consider the non-commutative deformation of the Coulomb branch. So in the physics literature, this is called omega background. So we slightly modified our construction. So we started with this picture. So disk times small interval, and we remove the point. But we consider this, we add a rotational symmetry to this picture. So we fix this axis, and we consider all the connections and all objects to be this equivalent invariant under this rotational symmetry. Then we can consider the corresponding homology group, but in the so-called equivalent homology group with respect to this S. Then still we can compose two operators by the same way, by considering the picture like this. But there's one difference. So in order to, when I try to explain why this multiplication is commutative, I just move these two balls in horizontal way and then switch the order. But if I assume the rotational symmetry, then you cannot move the two balls in horizontal direction. So it means that you have the monopole operator here and monopole operator here, but you cannot switch the order in a smooth manner. So it means that you don't have the explanation of why this is, you lose the explanation. Multiplication is commutative. In fact, you get non-commutative algebra in this way. And so this gives a non-commutative deformation. In fact, Coulomb branch or its coordinate ring is Poisson algebra. And this Poisson bracket is given by this non-commutative deformation. Once you have the deformation to non-commutative direction, then you have a two function f and g, then extend to non-commutative and take the commutator. And if you recover to the deformation zero part, then you take its leading part. So this is the Poisson bracket. And you can show that this Poisson bracket is a symplectic on the smooth locus. And in fact, Bellamy recently proved that this Coulomb branch with this symplectic, this Poisson bracket and the symplectic form on the regular locus gives an example of the symplectic singularity. So you can produce many examples of symplectic singularity in this ways, and also I think my interest is in representation theory. So I think it is very interesting problem to consider the representation theory of this non-commutative deformation. So the representation. So if my intuition. It is Z of sigma topological quantum field theory intuition is correct. Z of sigma is a representation of this Z of S2. And of course, once you put the rotational symmetry, the Z of sigma is not compatible with S1 action. So you cannot expect Z of sigma to be representation of the non-commutative deformation. But you can slightly modify the construction if there's once you can really get you can define non-commutative deformation in this way. Then I think there are various ways to produce its representation by a similar or slight modification of this construction. So this is a very interesting direction to pursue, I think. So, for example, I consider the special case, and for example, so this m equals 0 case, Hiraku kind of think about already consider the corresponding quantization. And I also study some other examples, and for example, Cherenkov algebra, the Brahman-Hecke algebra appears as an example of this non-commutative deformation of the Coulomb band. So it seems that we really get interesting algebra, sometimes non-commutative algebra, but sometimes maybe new algebra will be obtained by this construction. So I think this is an interesting direction. Thank you very much for watching.